Hi, everybody. Thanks again for tuning in today. Hopefully you all can hear me well. I know that Abel can hear me, so that means that probably everybody else can hear me. I'm super excited to introduce our seminar speaker this week, Professor Abel Méndez, who is currently an associate professor and the director of the Planetary Habitability Laboratory at the University of Puerto Rico at Arecibo. Professor Méndez is a planetary astrobiologist whose research has focused on developing theoretical habitability models, detecting and characterizing potential habitable exoplanets, and also works on radar observations using the Arecibo Observatory. So in essence, the goal of his research is really to map the habitable universe, and that's really how I've heard him describe his research. He received both his bachelor's and master's from the University of Puerto Rico at Mayagüez in physics and biophysics, respectively. And interestingly, he started off his academic journey studying theoretical high-energy physics at Fermilab before he switched to biophysics and astrobiology, of course. Outside of research, Professor Méndez is also quite active in public engagement and in outreach, and he really does love sharing his passion for astrobiology to the world. And so we're really fortunate to have him share some of his research today. Welcome, Professor Méndez. Take it away. Again, super excited for you to be joining us.
Thank you, Francis. Thank you for the invitation. Okay, let me start by trying to share my screen. I just need confirmation that you can see my first slide.
Perfect.
Okay, yep. Thank you. So I am Professor Abel Méndez from the Planetary Habitability Laboratory at the University of Puerto Rico at Arecibo. I will be talking about habitability models in astrobiology. These are models we are developing with many colleagues to study the potential for life in the universe, from microenvironments to global biospheres. Planetary habitability is an old problem. In 1883, William Miller pondered that the habitability of stellar planets, which is an old name from exoplanets, could only be determined relative to Earth. We know many factors of the planetary and stellar factors driving planetary habitability. And the problem here is how to define, the big problem in habitability is how to define habitability, how to quantify it, and how to combine the effects of multiple variables. So this picture shows that we have for each planet, you have planetary properties, stellar properties, and the planetary system as a whole. So there are many properties that you have to consider just to think about habitability. Here are some common misconceptions about habitability. First, that we can define it because it's a very abstract concept. That we cannot quantify habitability because probably it's too complicated. And finally, that we cannot access the habitability of faraway worlds because we don't know all the details of these environments. But I have the ability to quantify the quantifiable, and that's what I will be dealing today. Here are 6 types of environments. We know that terrestrial ones are habitable, and we presume that the planetary ones, Mars, the Moon, and Venus, are not. The only way to determine if any of these places are habitable in the common sense is by finding or putting life on them. But the purpose of habitability assessments is not that. It's to understand why the difference between these environments, why some places are better, also why some are worse. In other words, habitability assessment help to identify and understand the key environmental variables or limiting factors controlling the abundance of life, and not necessarily designing to tell if they are habitable or not in the common sense. I started asking myself about how to define and measure habitability around 20 years ago in the early days of the astrobiology field. I started by looking for a definition, including one beyond the astrobiology field. Most dictionary definitions were associated with human habitation. And strangely, this topic seems important enough, deserving a whole chapter in biology. But to my surprise, the words habitable and habitability were not generally present in biology textbooks. Therefore, I thought, like everybody else, that the topic of habitability was a new problem or question in biology brought by the astrobiology field, that the biological concept of habitability was exclusive an astrobiology topic. The first astrobiology paper to directly address how to quantify habitability was published by Chuck and Holland in Astrobiology in 2007. They suggested using the available power for life, or energy per time, as the best proxy to quantify habitability. A paper around that time, also by Tori Hogler from NASA, also concurred with using energy to quantify habitability. I was fascinated with this idea, but not totally convinced it was the final solution. Then, around 2009, I found something very interesting. I found a 1993 paper by Rice and others, not related to astrobiology, but using the word habitability to refer to the quality of a semi-arid land for some types of birds. The paper also pointed that their model was consistent with the Habitat Suitability Index used in ecology. So I searched for this habitat suitability and went to the source, and I was overblown. I finally realized that what astrobiologists call habitability, just a general term, as a new problem, was actually an old problem called habitat suitability in biology. In the late 1970s, ecologists were using different measures of habitat quality, not all consistent between them. Same problem astrobiologists are having today. Then, by 1980s, the U.S. Fish and Wildlife Service decided to fix this and created a standard described in their white paper, Habitat Suitability Index Models. I then realized that the problem of defining and quantifying habitability was already solved by biologists. So let's formalize some basic concepts of habitability. Habitability is defined as the suitability of an environment for life. This is the biology definition. Is proportional to the carrying capacity. So this is how we measure it, which is the maximum stable biomass that an environment can sustain. This is how we quantify habitability. Finally, habitability is used to determine how a set of environmental factors impact life to their presence or abundance. The key thing about this statement is that the set of environmental factors are not necessarily the only important ones, but the ones you want to understand. So you don't need to have all the information about the environment, because you're not trying to answer the final solution that is the place that is habitable or not. You just want to understand what particular factors that you know affect life, or factors that are the only ones that you can measure how they impact life. So here's the general equation. Here's the general equation used to quantify habitability in biology. And the study conditions are based on a set of variables of interest compared to some standard. And this is very important. Always you measure your habitability relative to some standard. And you just want to make sure that this proportion has to be proportional to the carrying capacity of the system of the study. So in practice, you construct a library of models, each for the specific environment and factors of life of interest. I love this analogy. Here's a powerful analogy for the requirements of life that is useful to understand the limit of life and habitability. Life needs the classical elements, air, water, earth, and fire, or more correctly, a gas, a liquid, a solid, and some energy. One of the reasons is that the elements necessary for DNA and other biological elements are not available in a single state of matter. So you need for them to be mixed together with a source of energy. And if we apply this to terrestrial environments, it's easy now to understand the abundance of life in terrestrial environments using the classical elements analogy. Forests have an abundance of these elements, therefore they can sustain a large biomass. Life is definitely visible in that picture. But when you look at deserts, ice caps, clouds, and the surface of the ocean or the deep ocean, and they have strong limitation on one or more of these elements. Thus, although they are habitable environments, the amount of biomass per unit of space and time never compares to that of forests. So the classical elements analogy is a good qualitative tool, but we can do much better and quantify our assessments. So we are working on an extension of the habitability models used in ecology, where habitability is proportional to the mass and energy available for life. Only a small fraction of the total mass and energy of a system is usually available for a biological process. Here in the red box is the differential expression where we can see the habitability H here depends on fluxes of mass and energy. And we can explore with this equation equilibrium conditions. It is always necessary to define a region of interest in space and time, for example, a patch of soil or a volume of water, or even a planetary surface, if considering the habitability of a biosphere. So you always have to define a space and time of interest for your model. Here in the blue box, is a very convenient way to calculate habitability relative to some other known environments and normalize in a scale between 0 to 1. This also helps to cancel out the quality factor Q, or the fraction of the mass and energy used depending on the mass and energy available, which is something most of the time it's hard to estimate. This assumes that the life form has the same ability to extract mass and energy from the environment of reference and interest. And this is not always the case. And finally, we can use the analogy of an electric circuit to understand how to combine many parameters in the equation. Unnecessary substrates, for example, from the gas, liquid, or solid phase, are used in parallel, and thus can be mathematically aggregated as resistors working in parallel. Then the total mass required for life becomes a reduced mass, constrained by the limited substrate from the available ones, and this expression reduced to the classic monod growth for one substrate. In our model, the first step is to pick the variable of interest and calculate the environmental fluxes or due to these variables. Here, the analogy of the classical elements just helps to organize them, for example, by those factors associated to the atmosphere, the hydrosphere, the lithosphere, and the available energy. we need then to apply a ecophysiology response curve to the model, which is the hardest part to do because in that part, this is the one that includes the biology. So when we deal with the mass and energy, we are considering the mass and energy of the environment. So we are doing physics and chemistry. But once we go to the ecophysiology response curve, then you are adding the biology to the model. And here is an example of a general model of an ecophysiology response curve that we can use to describe the effect of many state variables on life, from microorganisms to plants and animals. Life is usually constrained by some limit for each variable of interest, x, and has an optimum at some value between this limit, a minimum and a maximum. In the first plot, a model for the shape factor of the x exponent has been successfully used to describe the growth rate of microbial life as a function of pH or water activity or temperature in plants. In plot B, using the same model but a different shape factor can be used to describe the growth rate of microbial life as a function, let's say, of temperature. So usually what you need to create is a library of these models, and there from the scientific literature, you have already many of these models similar to this one or different, but basically doing the same thing, trying to relate individual variables and the effect and the growth on the or viability of some particular species. But here is just a general form. So now we can apply our models to the previous example of terrestrial environments and the classical elements with respect to available water, nutrients, and temperature. We get that forests are the most habitable places in our planet. That is, more mass and energy are used by life, while clouds are the worst habitable environment in our planet. Therefore, we went from a qualitative description to a quantitative description of the general habitability of some terrestrial environments. And here, I want to be more specific and present to you how to construct a habitability model, and this applies to the surface of Mars as an example. The first step is to select a space and type of interest. Here we are taking Gale crater because we have data from that location by probes. We select then in step 2 some variables interest. Here surface temperature and relative humidity because we know these two quantities and by measure, and we know how they impact life. And we then select in step 3 microbial life as our life of interest. At this point, we could look for any known ecophysiology response curve for any of our variables of interest, temperature or relative humidity. So in this particular case, we are omitting this part because if we do, we will conclude that Mars is not habitable by any standard at the surface based on this surface temperature and relative humidity. I will explain this a little bit further. So in step 4, we pick a standard of comparison, and the standard of comparison is the Atacama Desert in Chile. This means that we are calculating habitability relative to this terrestrial environment. We then, in step 5, parameterize our variables into our mass energy model. The key here is to find how your variables relate to the mass and energy and quality of the environment. And this is usually not hard to do. But the Q parameters enclose the information about the quality of fraction of the environmental life. And that's where the ecophysiology curves takes place. Finally, we try to validate our model is possible with a standard of comparison. And we did already that this a similar model with terrestrial biomass. So in this optional step, but if you are proposing a habitability model, make sure it works for Earth first. And here we apply this model, and the equation is at the bottom here of the plot. And for all possible temperature and relative humidity variation for Earth and Mars. So the spatial region here shows no condition necessary for life as we know it. Temperatures about 18 degrees Celsius, and water activity is about 0.6. So the problem here is that if you consider a ecophysiology response curve for any particular terrestrial life, it will tell you that it is only this box here. It will be the only the spatial region box, the only region habitable. But if we don't consider that, we can see and compare for life as we know it and as we don't know it. What is the mass and energy available compared to that spatial region? So assuming like there is a life that can use any of the states available, any of the temperature and water states available. And here is in red is data from Curiosity for the Great Crater. So all these points show you what is available in one particular location on Mars. The yellow here is a GCM of the surface of Mars, all conditions from globally. And green here is a little bit of data from Phoenix, and the blue region here is the Atacama Desert on Earth. So you see that there is a big difference of the Earth terrestrial environments here, the Atacama Desert and the Martian environment. And because in the scale at the right, we calculated this habitability, we can say and compare the average condition and say that the Mars is about 1,000 times less habitable than the Atacama Desert, even considering just temperature and available water. So assuming that there is any hypothetical life form that can sustain a biological process on these extreme conditions, it will be limited 1,000 times by the mass and energy available for life. So this is a fine way to say not habitable. And this is not including other factors like UV radiation, which actually make it worse. So at least by temperature and available water, we see how bad is the surface of Mars. And that's one of the applications of a habitable model, at least with respect to those variables. Looking at Mars in more detail, in the bottom plot, here's a thermal humidity habitability for two different Mars sols and a cave crater using data from Curiosity and compared to the Atacama Desert. These temperatures and humidities are too low for life as we know it, so we are not including the response curve because otherwise they will be zero because they are attached to terrestrial life. And we just want to compare the environments. We noticed that both hot and wet sols, the total habitable time per day is around the same, about 9 hours, and peaks close to 3 to 4 hours afternoon. Nevertheless, upper habitabilities are over 1,000 times less than anything in the Atacama Desert. So again, even if there is a life form that tolerates these conditions, these temperature and humidity extremes, as life as we don't know it, it has over 1,000 times less water energy resources than the terrestrial case Atacama Desert. Again, another polite way to say non-habitable by using the common sense. And suppose we start to learn more about exoplanets, like their size, their atmosphere, and water content. Something that we might be able to do in the next decades. then we might be able to compare this planet in terms of the potential for life. So now the same model, the same mathematical framework, the same steps are here applied to exoplanets. And in our first step is to select a space and time of interest. So now we are taking the global near surface layer of the planet as our region of interest. And we select then in step 2 some variables of interest. Only radius is known for mass exoplanet, but the other variables like surface temperature, pressure, and ocean fraction can be modeled from, for example, a general circulation model to explore potential scenarios. In step 3, we take here that this is habitability for primary producers. So on land as our life of interest, since they are the base for other life forms. In step 4, we pick a standard of comparison. In this case, the same Earth surface as a comparison standard. So we are comparing the surface of Earth, global surface of Earth, with global surface of any planet. We then in step 5 parameterize our variable into mass energy model. And the key here is to find again how your variables relate to the mass and energy and quality of the environment. Usually this is not hard to do. And finally, we try to validate our model. We don't have the luxury to validate our model with any other global biosphere in the universe. We did it with Earth by creating a 2D version of the model that correlates with current capacity. We found a linear relationship between our habitability model and net primary productivity, that is biomass produced by unit space and time. So we know the model, this kind of model works for Earth, at least Earth divides in a grid, into the grid. This means that our model of global biosphere habitability can be used to constrain the potential total biomass relative to Earth that can be producing an Earth-like planet, at least with respect to these simple variables. Temperature is one of the important factors, and I told you that we know the radius of the planet, but the next parameter we need surface temperatures, and we don't have that. So we're taking special attention on how to model temperature for exoplanets. So in 2017, we explored the effect of eccentricity and discovered that the mean global equilibrium temperature of a planet decreased with eccentricity, contrary to what is initially expected. Equilibrium temperature estimated with the average stellar flux of a distance, as shown in this plot here, and equations in the right, suggest that they should be higher. But this is not a correct way to calculate these temperatures. So we found out how to estimate the average equilibrium temperature for planets in eccentric orbits and in an effective thermal distance, which is something that, because the planet is in an elliptical orbit, we can define from any elliptical orbit a circular orbit that we can use to test out if this planet is in the habitable zone or not, because it's coming inside there too hot and it's moving away from the habitable zone and it becomes too cold. But we can always define this auxiliary orbit just to get an idea of what will be the actual average temperature of this kind of planet. And from the equilibrium temperature, we can get the surface temperature of the planet if we know a few things more, like the bond albedo and the normalized greenhouse. And we are exploring how to calculate this, and we discovered that basically the surface temperature of the planet is proportional to the equilibrium temperature for zero albedo multiplied by a factor K, and that factor K depends on the atmosphere of the planet, but also in the total pressure of the planet. And pressure is one of the parameters that we also need for exoplanets. So given their temperature and pressure, we can use this information to assess the habitability of any planet. And the problem is, as I already told you, that we don't have this information. So this only works for estimates. Here we see a plot of the result of many 1D to 3D simulation of planets in a plot of surface temperature versus stellar flux. Most of these planets have this factor, kappa, of 1.25, correspond to planet with dense CO2 atmospheres, about 10 bars. This type of model provides a simple analytical expression to constrain the surface temperature of the planet, given its surface pressure. So if you know the location of the planet, its orbit, then you can constrain what surface temperatures are possible depending on the total atmosphere, and depending on composition and the total pressure. So the zero albedo equilibrium temperature on exoplanet is similar to the surface temperature of a rocky world with a thin atmosphere. And if we apply this, here in red, we constrain the surface temperature of the 7 planets in the TRAPPIST-1 system. This is a exoplanetary system, very famous, 40 light years away. Assuming the albedos and greenhouse for none to thick atmosphere. So we try in this model different possible, well, exploring all the range of possible albedos and greenhouse for atmosphere less than 10 bars of CO2. If we then we can constrain what will be the temperature range. So at the x-axis is the stellar flux, and the y-axis is the temperature. And you can see that red line here is the range of possible temperatures. Also in green here are upper habitability limits using our habitability model. Given that we know and accept these properties, we can also establish as a range of possible. And we can see the possibilities.
It's 12 o'clock.
So, okay, thank you. Only planets D and E have a non-zero value, with E slightly better, but lower than Earth. So how we can interpret this? For example, we could say that any biosignature signal, if any, is more likely to be stronger in planet E than D. If we find the reverse is true, then this might mean that a different biology is at work here, since our model was based on terrestrial biology. So habitability models like this help to interpret and add context to any biosignature detection, something that we will try in the future. So more specifically, why habitability models? Why we need habitability models? First, to determine the relevance for life of one or more environmental variables. For example, a challenging problem, let's say you want to quantify the importance of life of magnetic fields for life. So usually what most of us think about a habitability model, so that the purpose is just to tell if the place is habitable or not. That is not correct. That is an oversimplification of what habitability models can do. And we can also select this model to select targets for observations, so follow the habitability, and to compare results from observations or models, for example, determine the global habitability of general circulation models, to provide context for biosignature detections. Habitability is possibly correlated with the abundance and diversity of life on Earth. But we don't know if this is true elsewhere. Also, to understand ecosystem on Earth and their potential elsewhere, from the solar system to exoplanets. And certainly, habitability models are not here to determine if planets are habitable or not, in the common sense. Otherwise, we wouldn't be using them on Earth. So these models are based and habitability assessment for terrestrial. We know Earth is habitable. So why we are using them why ecologists are using them. They don't need that. They just want to understand the relation between the environment and life. So in conclusion, habitability is already defined and quantified in biology. Astrobiology have been stuck in this problem, but now we can move forward with the next problem, modeling, applying habitability models. Habitability is formally defined as the suitability of an environment for life. It is quantified as a quantity proportional to the biological carrying capacity or the available mass and energy for life, which is an extension by our models. This model helps to integrate and characterize the effect of life of one or more planetary stellar parameters. A library of habitability models for different locations, parameters, species is usually created to study the system. It's not like the general idea that if you are trying to explore and using habitability model, first, like trying to determine the place is habitable. No, what you create different models, different variables. It's not to create a single model, but many models taking a set of variables at a time. So like it's like creating a library to understand the system. And very important, habitability model is an emerging field or re-emerging field. This is a new tool with so many applications. More information about our work is available in our recent review paper in astrobiology and a white paper submitted to the Planetary Science and Astrobiology Decadal Survey. I want to thank all our colleagues. We are a group. We call ourselves the Planet Hub Collaboration. And we are trying to make sense now that we have all this background framework to measure and understand habitability more precisely. We are trying to apply it to different scenarios, from terrestrial or string environments on Earth to the solar system and to exoplanets. And part of our team is Frances here. Thank you, Frances. And we are looking forward for many other scientists to join in. Especially, we need more ecologists. We are working with ecologists, but definitely we need more ecologists, which are the spare experts on terrestrial habitability. So thank you very much, and I open to questions.